Okay, so looking at the intersections of planes in 3D space. Typically, 3 planes in 3D space will intersect at a single point. But there are times this does not happen. There are times this doesn't happen. So sometimes we can get no solutions. And configurations of planes where there are no solutions is that perhaps 2 planes are parallel and the third one is at an angle. So there's no point where all 3 planes meet. There's a line where this plane and this plane meet, and there's a line where this plane and this plane meet, but those 2 lines are parallel, so those 2 lines never meet. So there's no solutions. All 3 planes could be parallel to one another. There's no solutions there either. Or they could form what's called a triangular prism. So this plane intersects this plane along a line, this plane intersects this plane along a line, and this plane intersects this plane along a line, but all 3 lines are all parallel to each other. And I'm drawing these diagrams, but they are very much cross-section of the planes. Okay. So yeah, these form a triangular prism. These are all parallel, and these are 2 are parallel. Okay. So there are situations where there are no solutions, just like in 2-dimensional space. 2 linear lines don't intersect if they are parallel, but we have 3 different situations in 3 dimensions. But we can also get infinite solutions. So this can occur when 2 equations are actually just the same plane. So 2 equations are the same plane. Just like if you try and solve 2 linear simultaneous equations in 2 dimensions and they are both the same line, then every point on that line satisfies both equations. It's a bit trivial, but it is a situation that we need to consider. Or we could have all 3 planes are the same. Again, a bit of a trivial case. This one here, there would be an infinite line of solutions where this plane intersects this plane. Have a look at my video on intersections of planes for that one. And this one here, because all 3 planes are the same, then the plane of solutions is that plane. There's not really much more to say on that. But the other situation, which is interesting, is similar to the triangular prism, but it just so happens that all 3 planes meet along a single line, and this configuration is called a sheaf. Okay, so we consider sheafs. These 4 are actually fairly trivial because it's really easy to tell if these are the case because you can look at the coefficients of x, y, and z. So we tend not to look at these too much, but these 2 are of great interest because triangular prisms and sheafs, they're not obvious but by looking at the equations, like these 4 are. So quite often questions will have this situation in them. Okay. So let's have a look at finding solutions. So typically, as I said, planes will intersect in 3D space at a single point, and this is exactly one of those situations. Now, if you have seen my previous video, then we will be able to find the, I can just state the inverse of the matrix, which I'm about to show you, because that is going to be necessary. So 1, x, y, z equals minus 17 minus 35, 11. So I've just written this set of equations as a matrix set of equations. Okay, excuse me. In other words, m times x bar is equal to a vector a. And what I could do is I can multiply both sides of this equation on the left by inverse m, assuming it exists, which I know it does in this case. And m to the minus 1 times m, they just cancel each other out. So I'm left with x, my unknown vector, is equal to the inverse of m times a. And that applies to 2 dimensions as well, so you would have looked at that in first year. So we just need to calculate the inverse of this 3 by 3 matrix. If you look at my previous video, I've already done that. So we've got x, y, z is equal to a third into 6, 1, 13, minus 3, 0, minus 6, 9, 2, 23. Okay, that was from the previous video. Times this matrix A, vector A, which is minus 17, minus 35, 11. So all you need to do is carry out this matrix product and then divide them all by 3. So that is going to be a third into 6 times minus 17, minus 35, plus 11 times 13. Gives me 6. In the y direction, I've got 3 times 17, plus 0, minus 66 is minus 15. And in the z direction, I've got 9 times minus 17, minus 70, plus 23 times 11. Gives me 30. So this implies then that x equals 2, y equals minus 5, and z equals 10. Those are solutions to the equations. And what you should always do with solutions to equations is just check that they work. So x was 2, so it's going to be 8, minus 5, minus 20 is minus 17, so that works. X was 2, so that's 10. Y was minus 5, so it's minus 35. And then z was 10, again minus 35, so it works. And then finally, minus 4. Minus 5 is plus 5, and then plus 10 is 11. So those numbers work with the equations, so they are correct. Okay. So that's how you would find the intersect of 3 planes. So the coordinates of intersection are 2, minus 5, 10. And don't forget that if the question asks you for the coordinates of intersection of 3 planes, you must state your answer as coordinates. If it just asks you to solve the equation simultaneously, then you just leave your answers as x, y, and z. Okay, make sure you answer the question that has been asked. Most common mistake. All right, well, what happens then if there are either no solutions or infinite solutions? So we can do the same thing here. We can split this up into a matrix. Times a vector equals the vector. And now we can just find the inverse of this matrix, right? So go to matrix mode. 3 rows, 3 columns, 3, 1, minus 5, 2, 2, 1, 1, 3, 7. Matrix A. Recall matrix A. Inverse it. Wait, there's a math error. And that is because the determinant of this matrix is 0. So this implies there are either no solutions or infinite solutions. We don't know yet. We don't know. There's either no solutions or there's infinite solutions. And actually, if there's no solutions or infinite solutions, it also implies that the determinant of the matrix is 0. So how do we decide if there's no solutions or if there are infinite solutions? And if there are infinite, how can we find them as a general case? Well, first of all, let's just check the rows of the matrix, make sure that none of the rows are multiples of the other rows. They are not. So because none of the rows are exact multiples of any of the other rows, then we must be of the form either of a triangular prism or a sheaf. Okay? No solutions or infinite solutions. Okay, we can't be of these because no row is a multiple of any other row. So it must be either a prism or a sheaf. Well, there's no other way but to do it by a bit of brute force. So what I'm going to do is I'm going to take these equations, make one of the unknowns a subject, and plug that into the other two and see if I arrive at a contradiction or not. So let's take this third equation and make x the subject. So that's x is equal to 17 minus 3y minus 7z. And I'm going to take that definition of x and I'm going to plug it into the other two. So I'm going to get 3 times that, so that is 51, minus 9y, minus 21z, so that's 3x, plus y, minus 5z, equals 12. Simplify that a little bit. I get minus 8y, I'm going to say 8y, minus 21z minus 5z is minus 26z, so it's plus 26z, and that's going to equal 12 minus 51, but then I'm minusing that, so that's going to equal 39. So there's one equation in y and z. Do the same thing now, plug in this definition of x into this second equation. That's 2 times x, so that's going to be 34, minus 6y, minus 14z, plus 2y, plus 2y, plus z equals minus 52. Simplify that, minus 6y, plus 2y is minus 4y, so I'm going to call it 4y, plus 13z, and that is going to equal minus 52 minus 34 times by minus 1, it's 86. In other words, 8y plus 26z equals 172. So that is a contradiction, because 8x plus 26z can't equal 172 and 39 at the same time, whatever value y and z are. So this is a contradiction, so therefore there are no solutions. Okay. There's no value of y and z which satisfy this. Therefore there's no values of x, y and z which will satisfy this. Okay, so therefore it must be a sheaf. So we can conclude, therefore, these 3 planes form, no, not a sheaf, sorry, a prism. A triangular prism. And sometimes you'll be asked to state the configuration of the planes. Okay, example of no solutions. And finally, this one here, which funny enough is going to be an example of infinite solutions. So again, well, we have the same matrix actually. 3, 1, minus 5, 2, 2, 1, 1, 3, 7. So the determinant of that is 0. So I'm going to have to do this by brute force. So again, I'm going to say x is 76 minus 3y minus 7z, and plug that into the other two. 3 times 76 is 228, minus 9y minus 21z, plus y minus 5z is minus 42. So I'm going to say that's 8y plus 26z equals minus 42 minus 228, and then I'm going to times up by minus 1. So that comes down to 4y plus 13z equals 135. Okay, that's one. Second one should come out to be exactly the same equation. And I know that because I've engineered this as infinite solutions. So I can take this definition of x and plug it into this one again. So 76 times 2 is 152. Minus 18y minus 42z. Oh, sorry, I'm looking at the wrong one here. Try that again. 152 minus 6y minus 14z plus 2y plus z equals 17. Minus 6y plus 2y is minus 4y, so times by minus 1. plus 13z, and this time it's going to equal 17 subtract 152, and then minus that is 135. So what we find here is that this is not a contradiction this time, because 4y plus 13z are both the same. They are both 135. So therefore there's an infinite number of solutions. These two lines are parallel. Okay? So we have a degree of freedom. We can choose. So I'm going to choose z to be 4. I'm going to choose z to be, I'm going to choose z to be lambda. So choose z is equal to lambda. Okay, you have a degree of freedom now. You can choose. Because of these two equations are the same, we have a degree of freedom, so that gives us a one-dimensional object, which is the line of intersection of the sheaf. So I'm going to choose z to equal lambda, and that's going to define for me y in terms of lambda. So this implies y must equal 135 minus 13 lambda over 4. Might look messy, but we can tidy it up a bit later if we want to. And then finally, we use these two definitions of y and z in terms of lambda to find x by using this relationship up here. So we get x is equal to 76 minus 3y. So that's 405 minus 39 lambda over 4. Minus 7z, so minus 7 lambda. (76) minus 405 over 4 is minus 101 on 4. And then 39 on 4 minus 7 is 11 on 4, plus 11 lambda on 4. So that's 11 lambda minus 101 on 4. So now I've got x, y, and z in terms of lambda. Therefore, x, y, and z equal x is minus 101 on 4, y was 135 on 4, z was 0, plus lambda times x, the coefficient of lambda for x was 11 quarters, for y was minus 13 quarters, and for z it was 1. So I could times that direction vector by 4 just to neaten it up. And I'll get x, y, and z is equal to, I'll probably find a neat one of those as well, but to be honest, I can't be bothered. 135 on 4, 0. Plus, I'm going to redefine my lambda to be mu. That's 11 minus 13, 4. The reason why I can do that is because this is the direction vector, so it's the direction that matters, not the magnitude, so I can times that by 4. Whereas this one is a position vector of something on the line, so I can't do anything with that unless I add or subtract multiples of this, which I'm sure I could do to make these integers, but it's unnecessary. So this is now the equation of the line of intersection. So this is the equation of the line of intersection. These three planes have formed a sheaf. Okay, and the line that intersect has equation